The reactants are absorbing energy. So we have a nitrogen to nitrogen triple bond here. We look on table 13.1 and you will see a nitrogen-nitrogen chemical bond. And it tells you that the bond energy is 942 kilojoules per mole. So we're going to write that down under energy absorbed, 942 kilojoules per mole. That is the amount of energy needed to be absorbed to break this nitrogen bond. Next, hydrogens. Okay, we're going to find the hydrogen-hydrogen bond, which is here. It tells us it is 432 kilojoules per mole. But there's not just one of those, there are 3 of those. So for energy absorbed, we're going to add 3 times 432 kilojoules per mole for the hydrogens. And that, once you multiply and add that out, that's how many kilojoules per mole of energy is absorbed. Now, my time is running out. I will finish this exam. We are picking up right where we left off in our last module video. So this is video 13C. And we were working on this example from 13.2. So we are trying to figure out the change in enthalpy, the delta H. And so far, we have put in the numbers for how much energy is absorbed for each of the bonds in this chemical reaction. So we have the energy levels for the reactants. Now we have to figure out or put in the energy that is released when these bonds are formed. So again, we look to table 13.1, which is on page 424. And looking at our products here, we have nitrogen, hydrogen, single bonds. And there are 1, 2, 3, 4, 5, 6 of them. So whatever the value for the nitrogen-hydrogen bond, we're going to have to multiply it by 6 because there are 6 of those bonds. Okay? Then looking at the table, nitrogen-hydrogen bond has 386 as a bond energy. 386 kilojoules per mole. Okay, so we've put in the bond energies for the reactants over here for energy absorbed, and we've put in the bond energies for the products, the energy released, and now it's just a matter of putting this into your calculators. So you would do the 3 times the 432 and add it to 942, and then take that total minus 6 times 386, and you would get a change in enthalpy of negative 78 kilojoules per mole. So that is how you use the table of bond energies to calculate delta H. Would this be exothermic or endothermic? That is right, it would be exothermic, meaning it gives off heat. Again, that might seem a little backwards, but remember this negative 78 refers to the compounds in the reaction. So the compounds are losing 78 kilojoules per mole energy and giving that off to the surroundings, meaning that the surroundings and like the beaker that you're working in or whatever you're working in is getting hot. So when it's a negative delta H, it's exothermic. All right, we're going to move on to the next section, which is Hess's law. And hopefully you have already read this section. I also have to change my page numbers. So we are now working from page 428 to 433. And as the book tells you, all the information on Hess's law gets a little complicated. So we are going to just take notes on the minimum, what you need to know from this chapter to understand from it, okay? So Hess's law, here are some things you need to know. First of all, we have this new symbol, delta H with a little F down here. This is the energy of formation, which is the delta H, or the change in enthalpy. Sorry, not energy, this is enthalpy. Enthalpy of formation, which is the delta H for a formation reaction. If you remember what a formation reaction is, it's just the individual components combining together to form a compound. Okay, so it's the delta H of a formation reaction. And then also we need to know that the standard enthalpy of formation, this little circle right here means standard, means that the formation reaction was run at standard temperature and pressure, which is 25 degrees Celsius, which is like room temperature, and 1.00 atmospheres. Okay, so the standard enthalpy of formation, you can write that in words if you need to, of an element in its elemental form equals 0. So remember, in formation reactions, you're going to see just individual elements as the reactants. You don't even have to look up the standard energy of formation for those elements, because they would just be a 0. Okay? And then finally, we are learning another way to determine delta H. So first we talked about how, or you put in your notes that you could determine it by doing the experiment, which would obviously be a difficult way to do it. Then you could use table 13.1 with the bond energies, or here is another way to determine delta H. This is another formula. The delta H, again, at standard conditions, I think I called it standard temperature and pressure before, which is STP, but STP is 0 degrees Celsius. So I should say standard conditions, which is like room temperature, which is 25 degrees Celsius. Okay, so the delta H under standard conditions equals, we have a new Greek symbol. This is a sigma, and it means sum of. I'll write that in down here. Equals sum of. And then you could also add into your notes that this means standard conditions, which are 25 degrees Celsius and 1.00 atmospheres. Okay, back to our equation that we're writing. The sum of the enthalpy of formations for the products minus the sum of the energy of formations for the reactants. And of course, we will do an example of this together. So we're going to do example 13.3. I think I have enough room on my whiteboard here, so I'm just going to try to write a little bit small and squeeze it in here at the bottom. Okay, example 13.3 says, what is, I'll write it in this time, what is the delta H under standard conditions of the following reaction? And the reaction is 2NO plus O2 yields 2NO2. All right, now let's start filling it in for the equation that we just wrote down. So the delta H under standard conditions is going to equal the sum of the enthalpy of formations of the products. Okay, so now we're going to look at a new table. This is table 13. Where are you? Aha. On page 431, table 13.2 tells you the standard enthalpies of formation in kilojoules per mole of some common compounds. Okay, so we're going to start with the enthalpy of formations of the products. The products in our reaction here, there's just one product. It's NO2. So NO2 under table 13.2, I see has a standard enthalpy of formation of 33.2. So first we're going to have, and I'm going to put the products in brackets out here, okay? 33.2, and that's in kilojoules per mole. But see how for the products there's not just 1 mole of NO2, nitrogen dioxide, there are 2 moles. So we need to multiply this number, 33.2 times 2. So I'm going to add a 2 out front for the number of moles. I'll write moles in here. So 2 moles times 33.2, that's going to give us the sum of the enthalpy of formation for the products. Now I'm going to subtract minus, and I'm going to put everything in brackets for the sum of the enthalpies of formation for the reactants. So one at a time. The first reactant is nitrogen oxide, and again, there are 2 of them. So I'm going to start by writing 2 moles times, now I'm going to look up the enthalpy of formation for NO. Table 13.2 tells me that it is 90.3 for NO. So this would be 2 moles times 90.3 kilojoules per mole. Okay, now I have to add my other reactant because I have 2 reactants, okay? This is just oxygen. Remember what I said about elements. Oxygen is just an element. We never see oxygen by itself. Remember, it's a homonuclear diatomic, so it's always O2. But that's just the elemental form of oxygen. Up here we wrote that the enthalpy of formation of an element, oxygen, in its elemental form, you always find it as O2 equals 0. So we're just adding this to 0. We're not going to find an enthalpy of formation on the table for oxygen because it's just 0. So now we just plug this into our calculators. 2 times 33.2 minus 2 times 90.3, and we will get a change in enthalpy of negative 114.2 kilojoules. So again, is this exothermic or endothermic? It's negative, so the reaction is losing energy, giving energy off to its surroundings, so it's exothermic. Exothermic. And if you can do problems like that for this section under Hess's law, try the on your own problems as well, and look at the other example as part of example 13.3. Try those on your own, but if you can understand how to do those, then you understand enough about Hess's law. All right, have a great day, and I will see you next time.